So we have so far talked about breakdown mechanisms in the three states of matter: gases, liquids, and solids. Now let us look at another insulating material, which is vacuum. Vacuum is a good insulator, and technically speaking, you would expect that vacuum would not break down because you need charged particles for breakdown to happen. In vacuum, you do not have any particles, so you really should not have a breakdown, and vacuum should be the best insulating material available to us. It does not happen primarily because it is very difficult to maintain perfect vacuum. I mean, you cannot achieve perfect vacuum, and even the kind of vacuum that is really insulating, to maintain those pressures are difficult. So let us see, let us have a little discussion about how breakdown happens in vacuum. Now, as I said, ideal vacuum has the highest possible dielectric strength because obviously there are no carriers to conduct current. So ideally speaking, vacuum should never break down. Uh, but that does not happen. For example, what are we talking about? Even at low, even if we do not have perfect vacuum, it could be good enough. For example, below 10 to the power minus 2 pascals, there are less than 3 into 10 to the power 12 moles per centimeter cube present, which means that the mean free path which is available to the particles is in the range of meters. So particles will be able to travel meters before performing collision. So it will acquire a lot of energy, but it will not perform collisions, and therefore no more carriers will be produced. But that is not what we are dealing with in real situation. Even low pressure is difficult to maintain. And another important thing is, apart from maintenance of pressure, vacuum should be vacuum. There should not be any particles. That's what we call vacuum. But vacuum will likely to be contaminated when you have the manufacturing process, or when you have vacuum in operation. It is very difficult to maintain its cleanliness. The vacuum will be contaminated due to the presence of the insulating and metallic surfaces, because uh, you can have vacuum, but you will still have the surfaces which will have to be cleaned. They have to be perfectly cleaned, and they have to be maintained clean. Very often these surfaces may have absorbed gases and oil vapors, and under electric fields these vapors may be released into the vacuum. So you start with vacuum, you think you have vacuum, but you don't have pure vacuum in place. Also, because of the presence of the electrodes, in the electrodes there might be contaminants, or even if there are not very large quantities of contaminants, due to the very high electric fields which you can apply on vacuum before it breaks down, you may be able to generate charge carriers by pulling them out from the neighboring electrodes. So in vacuum, the reason for breakdown is generally because we cannot maintain ideal vacuum, either in terms of pressure or in terms of purity. Now, when you have a vacuum insulation, before breakdown happens, there will be pre-breakdown currents which will flow, because unless you have charge carriers present in the vacuum, you wouldn't have breakdown. So there are always pre-breakdown currents for small gaps. And when I say small gaps, I mean gaps less than 2 millimeters. And if you apply small voltages, then a very small steady current will begin to flow. And this current is likely to be due to electrons. So electrons are generated either from the electrodes or from the vacuum gap, and a small steady current is established. And this will ultimately lead to breakdown. When you have larger gaps, let's say greater than 10 millimeter, then not only currents begin to flow, the current may not be immediately a steady current. You may not have sufficient charge carriers to establish a steady current through the gap, but you will see quasi-steady current, so that there will be current pulses flowing and which will die out, or there might be even micro discharges, small discharges happening, and then a quiescent period follows, so that you don't have any current. Ultimately, after a period of this quasi-steady current flowing and micro discharges happening, the current will become steady. Once the current becomes steady, that depends upon the size of the gap. Once you have established a steady current, even across a large gap, as you increase the voltage, the current will firstly become steady, and then the currents will rise and breakdown may occur. So in both cases, even for small gaps or for large gaps, breakdown is possible, and before breakdown happens, a steady current will have to be established. A steady current is more easily established by electronic currents in a small gap, in a larger gap. Before you can establish steady current, you will probably have quasi-steady current flow, or you will have micro discharges. How do these charged particles enter into the vacuum gap? There are various processes by which electrons can be injected into the vacuum. One process is from metallic protrusion. So you have electrodes, and from the electrodes there might be irregularities on the surface. There may be very minute protrusions, and these minute protrusions will have a high field intensification. There will be high flux concentration at their surface, and because of that there might be electronic charges being emitted. So this process is known as Fowler-Nordheim cold field emission. You don't need high temperatures, you only need high fields. So a current begins to flow due to electrons being released from the metallic protrusion. The current density from a sharp electrode can be expressed as a function of electric field as J, the current density, equal to AE square exponential to the power minus B phi to the power 1.5 V as a function of y being the distance, and E being the applied electric field, ampere per meter square. So as you can see, the current is dependent on the work function of the metal. So depending upon what metal you choose for your electrode, it depends on that whether you are likely to get currents, high currents quickly, or breakdown is likely to happen. So you see here, it is not the vacuum which is determining the breakdown, but the electrode property which determines whether breakdown is likely. Other sources of electron, apart from the pure metal of the electrode, it's a protrusion, but it's a pure metallic protrusion. Other sources of electrons could be oxide films, which are present on the surface of the electrode. There may be trapped positive surface charge, which will be released due to application of the electric field. Adsorbed particles on the cathode surface. So it's not perfectly clean, and these particles are released. There might be local hotspots. So when you apply the electric field, if there is any irregularity, there might be small regions where there might be overheating and hotspot formation. So essentially what you need is, you need clean conditions. When you have clean conditions, field emission is the only source. It says here field emission. We are not talking about any field emissions. We are talking about, I'm sorry about this, we are talking about field emission. So if you are able to control the vacuum, if you're able to control the electrode surfaces, free them from all kinds of impurities, oxides, etc., then the only source from which you can have current is through field emission. Fields emit assistant ionizing collations in metal vapor. If, for example, the electrode at high field vaporizes, so it becomes a metal vapor, and this metal vapor can, under the application of the field, cause ionizing collations with other random particles present in the vacuum gap. This can ultimately also lead to breakdown. Apart from the metallic electrodes, you can also have electron emission from non-metallic surfaces. So one way to prevent metallic emission is to prevent Fowler-Nordheim is to coat the electrodes with a insulating layer. And we do that. Insulating and semiconducting layers are created on the surfaces, but these insulating or semiconductor layers may slow down the electronic process, but they are also liable to cause electron emission into the vacuum gap. Apart from that, there might be dust, there might be micro occlusions on the electrode surface, that is, small particles or small gas bubbles might be occluded in the semiconductor layer. So to protect the metal, you might add an insulating or semiconducting layer, and this layer then becomes of a problematic nature. We also do not like to have very large area electrodes in vacuum, because if you have large area electrodes, then they're likely to be contaminated with dust, with oxides may be formed, adsorbates might be there. Remember, oxidation in vacuum takes place faster than under normal pressure. At high fields, the electrodes may also undergo chemical reaction due to electron on ion impact. Adsorbed particles may be released from the surface. Micro discharges may happen due to particle bombardment. Secondary electron emission may happen. So as you can see, most of the activity is taking place at the surfaces, but not in the vacuum. But no matter, if you have enough charged particles, this can ultimately lead to breakdown. So what you have is, you will generally see, as I said, right away, unless it's a small gap, right away you do not have steady currents flowing in the gap, you have micro discharges. What are micro discharges in vacuum? Generally, when we talk about micro discharges, we are talking about low power pulses, which have durations of 0.1 to 100 milliseconds, and they are of also very small magnitude, less than 100 milliampere magnitude, and they are not self-sustaining. These micro discharges can be caused by various factors, various reasons. There can be small particles of the electrode material which are pulled out of the electrode under the application of the electric field. So these electrode materials, small chunks flow out, and when the small chunks enter into the vacuum, they will be accelerated by the applied electric field, and they will go and strike the other electrode, and as a result there might be emission from the other electrode. So once you have a problem, this can lead to a runaway process. That's one way, where you have small chunks of electrode material pulled out and accelerated in the electric field. In the cathode, if you have a cathode emission, then beams of electrons from the cathode can vaporize small quantities of material from anode or the cathode surface. So the cathode electron beam will be transferring energy, and because of the energy of the electron beam, what might happen is small quantities of the material can be immediately vaporized. So you have a metal vapor introduced into the vacuum gap. Positive or negative ions may be ejected from the electrode surface, less often from the metal and more often from contaminant films. So all these can lead to small micro discharges taking place inside the vacuum. When a gap is caused to break down repeatedly in vacuum, now depending on so many factors, depending upon what is the size of your gap, what is the electrode material, whatever you have, so many factors, a particular gap, vacuum gap, will be able to break down, may break down. And this is a particular breakdown voltage. It happens at a particular breakdown voltage. This you cannot predict. It depends upon many factors, because vacuum is not supposed to break down. So these are the other factors of impurities, oxidants, etc., which determine when that vacuum gap breaks down. So initially you have a stable current or micro discharges, and after that breakdown of the vacuum happens. But funnily, if a particular vacuum gap is allowed to break down, so you raise the voltage to its breakdown voltage, you allow it to break down. After some time, the vacuum regains its insulating property, you allow it to break down again. You do it a number of times, and that has its advantage. What advantage is that? When a gap is caused to break down repeatedly in vacuum, breakdown voltage increases with the number of shots. So you first breakdown may be at a low voltage. Next time you apply the same voltage, breakdown does not happen. You can go to a high voltage. This happens for a number of shots. And with this number of shots, you find the breakdown of the voltage vacuum gap increases. The breakdown voltage increases. So it becomes capable of withstanding higher voltages. Why does this happen? This is a good thing to happen because you are kind of raising the breakdown voltage. Of course, it does not go on increasingly infinitely. After a number of shots, it reaches a steady value, and this is called the steady conditions value. And why does this happen? It is because, as I said, there are many random factors which lead to breakdown in a vacuum. And when you apply the first shot, these most vulnerable regions, if there is a protrusion, if there is an irregularity, if there is an adsorbed gas, all these random factors come into play, and they are the reasons for breakdown. So when this protrusion, a micro protrusion, causes a discharge, a micro discharge, and leads to a breakdown of the vacuum, that particle is released. So now you're left with an electrode which does not have any protrusion. So by the process of breakdown, you are able to remove, or you're able to smoothen the random micro protrusions or the surface conditions which are likely to lead to breakdown at low voltages. So once you get rid of these through breakdown, you are able to achieve a higher conditioned value of the vacuum gap. There are many factors which influence the breakdown voltage, like electrode separation, electrode material, surface finish, pressure, voltage waveform. Let's talk about electrode separation. If you have small gaps with very clean electrode surfaces, you will see that as you increase the voltage, bright spots of light appear at the anodes. This is because there is cathode emission and the electron beams which are reaching the anode from the cathode, they cause thermal radiation at the anode and hotspot formation happens. So in those small regions at the anode, spark breakdown happens. When that is sustainable, then ultimately this can lead to breakdown. This is true for small gaps. So you have small hotspot formation of the anode, and that ultimately leads to breakdown of the entire gap, would really be possible if you have small gaps, and this happens with clean electrode surface condition. You would have a relation of the breakdown voltage which is given by VB equal to K into D. So D being the distance of the gap and K is a proportionality factor. The linear relationship between the breakdown voltages with the distance tells us that the process that is involved is the field emission process. In this case, you need breakdown stresses as high as 10 to the power 8 volts per centimeter. If you have large gaps, which means gaps larger than 1 centimeter, then field emission currents are not enough to cause breakdown. And breakdown occurs with localized spark channel. So there would be a spark channel which is created at a particular location, and that small spark can ultimately lead to breakdown. But this is generally not due to field emission. The sparks must be due to some other reasons. In this case, the breakdown voltage can be lower than 10 to the power 4 volts per centimeter. And here you do not have a linear relationship, you have a power law relationship. So the breakdown voltage is related to the gap distance as Kd to the power n. And K and N are constants which are given by the electrode and surface conditions. Electrode material would have a strong influence because, of course, electron emission would depend upon the work function of the material. So the contact metal is the correct choice of the material is important. Electrode geometry is very important because larger the surface area, less possible it is to maintain uniformity, to prevent oxidation. So larger the electrode area, lower is the breakdown voltage. Surface finishes, of course, are very important. It has to be clean. If you have insulating films formed on the electrode surface, the breakdown voltage will be higher because the insulating film will be capable of suppressing field emission. So surface finish of the electrodes is of great importance. And lastly, we are talking about vacuum, but we would not have perfect vacuum. It's not like you would have no particles present, even if you were able to prevent all these electrode emission processes and vaporization, etc. Even then, to start with, you have a problem because when you talk about vacuum, you're actually talking about a low pressure gas. So there is always a finite residual gas pressure. If you have gaps less than 1 millimeter, and if you have gaps and if you are able to reduce the pressure, of course the breakdown voltage improves. However, if you have gaps less than 1 millimeter and if you have a pressure of 10 to the power minus 2 pascals, that's it. Reducing the pressure further is not going to help you. But if you have large gaps, then pressure has a significant influence, and if pressure is increased, breakdown voltage decreases sharply. It is still not clear exactly why this happens.